you can see my presentation in the screen. So if you're okay, you just give me, you can hear like my presentation is visible. Okay. Okay, so today I will be talking about tides and its numerical model. So myself, Jithin, I'm working at INGOIS as a project scientist. So this is part of training course on fundamentals of ocean modeling conducted by ITCO Ocean INGOIS. So barotropic tides in the ocean. So tides are the periodic rise and fall what we see on the ocean surface, which are generated as a response of gravitational force exerted by the moon and sun and the combined rotation of Earth-Moon system. So as in this GIF, you can see the movement of water at the coast. So the periodic rise and fall of this water level is manifested as tides. So here you can see the time series of time evolution of sea surface height during each period of tides. So there is a low tide period, and when the elevation is maximum, it is called high tides. And associated with this vertical movement of sea surface, there is also horizontal movement of water body. It is called tidal currents. So during when the tidal flow comes to the coast, it is known as flood current, and when it retracts from the coast, it is known as ebb current. So this ebb and flood is more clearly visible in the estuarine and lake inlets. We can see this very strong moment of flood and ebb current during each tidal cycle. So these oscillations often shows different characteristics all along the different coast. So it means that the nature of this tidal elevation or oscillations is not uniform. It varies from one location to another. Usually, in some location there will be it is two highs and two lows, and in a day it is called semidiagonal tides. So the tidal elevation will be look like this. So there will be two highs and two lows in a day. So that is called semidiagonal tides. In some areas there will be only one high and one low during a day. So those tidal oscillations is called diurnal tides. So here you can see that diurnal tides, only one high and one low. And in some locations, the tidal oscillations will be having a mixed nature. So there will be two lows and two highs, but the two lows and two lows and highs will not be equal. So there are unequal low tides and high tides. So here we can see that very high tide is there, and then low tide and lower high tide and higher low tide. So this figure shows where the nature of the tidal oscillations all along the globe. At some locations where the semidiagonal tides, it is represented as red line along the coast. In the, for example, for the Bay of Bengal area region, so the tidal oscillations is semidiagonal, and in the Arabian Sea area, the tidal cycle is like mixed in nature, and there are some area with the pure diagonal and semi-diagonal tides, such as Gulf of Mexico and the Pacific, Western Pacific near the Indonesian area region. Okay. So these tides are generated as a response of gravitational force and combined rotation of Earth-Moon system. So this animation represents how the Earth-Moon's system revolves around a common center known as barycenter. So this uh, barycenter, the center of mass between this Earth and Moon, lies inside the Earth because of its large mass. Uh, this mass of this Moon is very less compared to the Earth. So the center of mass lies inside the Earth, but not the center of the Earth. It is near to the center of Earth. So this is called barycenter, and this Earth and Moon revolves around a common barycenter. So this creates a centrifugal force and gravitational. So this motion will be balanced by centrifugal force and gravitational force between Moon and Sun. So here these points, when the Moon revolves around the Sun, we can see that this Earth-Moon system revolves around this barycenter. And the tide generating force is generally aimed as the difference between these gravitational and centrifugal force. Here, in some, due to this centrifugal force is essentially originated due to the motion of Earth-Moon system around the barycenter. Note that it is not the centrifugal force which are generated like two body rotations, but its center is on the inside the Earth. Here we can see that in this area where the Earth facing the Moon, the gravitational force will be larger than the centrifugal force. So there it will create a bulge towards it will create a bulge to tide generating force towards the Moon side, and in the opposite side of this Earth, the centrifugal force will be same, but the gravitational force of Moon will be lesser due to the greater distance in the opposite sides. So there also a there also will be a difference in the balance between these forces. Then that creates the tide generating force in the opposite sides. So I'm not going in detail to the derivation of the tide generating force and all, but note that the Earth-Moon system is kept in a dynamical equilibrium between these two forces. So the first force is centrifugal force, and the second is the force of gravitational attraction between the Earth-Moon system. And the horizontal component of this tide generating force creates the tidal bulges in the ocean, and it is can derive from the equations of between these tide generating force gravitational force and centrifugal force. If you want to go the detailed derivation of this uh, tide generating force, you can refer this book, The Oceanography of Tides by Sigmund and Kovlik and John Luke. So if you are interested, you can go through this book. There is a detailed description and derivation of this tide generating force. So next we are going to talk about the spring-leaf cycle of tides. So now we know that the tide generating force is due to the combined rotation of Earth-Moon system. And for simplicity, we earlier only talked about Moon. So there is also gravitational attraction from the Sun. So when the Sun and Moon and the Earth comes in the same alignment, so it gives the maximum gravitational force attraction, that means generating force. So during those times, the tidal elevation will be maximum. And when the sun and moon and earth is in perpendicular alignment, so the the tide generating force will be lesser. So during that period, it will create a very low tidal oscillations. Those period is known as neap period. So here we can see that spring neap cycle of the tidal tides over a period. Uh, the spring neap cycle occurs every 14.76 days. Uh, Similar to the variation in the tidal elevation, there will be also changes in the tidal currents similar to this elevation. So in the elevation as well as in tidal currents, you can see this spring neap cycle. So this is the spring neap cycle and the tidal ranges. Here we can see that the largest tidal range occurs during the full moon and new moon, where the tide, moon, and sun are in the same alignment, and this will be the high. During that time, high tide and low tide will occur, and during neap period, that tidal ranges will be uh, smaller. So then high tides and low tide will be seen during that period. So as we said, these tidal oscillations are related to the periodic movement of celestial bodies such as moon and sun. So these oscillations, so these tides are related to the oscillations of this body. So the tidal variability uh, can be represented in terms of their periodic movement. So the tidal variability can be represented as a sum of different constituents. Each constituent represents periodic change or variation in the relative position of the earth and moon and sun. So these frequencies essentially determined by the cycles of motion of moon and sun and earth. So these are the major tidal constituents, M2, S2 and N2. This constituent known as semi-diagonal because it has a periodicity about 12 hours, half a day, and this K1, O1 and P1 is known as diagonal constituents. It has a period of about a day. See this, and there are, apart from these diagonal and semi-diagonal constituents, there are long period tidal constituents known as MF and MM and MSA. These are related to the movements of moon and semi-annual cycle of sun and monthly cycle of moon. Note that these are only the major tidal constituents. There are hundreds of minor constituents, but for the most of the practical applications, these 10 or 12 major tidal constituents are enough to predict the tidal elevations at a particular area. But there will be exceptions, particularly near the coastal regions where the narrow channels or estuary. So there the complex or non-linear times tide will be dominate. So in that area, minor constituents also be important. And one of the method to extract these tidal elevations from the observations is harmonic analysis. This is a mathematical process to extract the tidal currents or tidal elevations. It's separated from the observations into basic harmonic constituents. So as we said, these tidal variations can be represented in terms of sum of finite number of harmonics. So using this Fourier analysis, we can extract the tidal signals from the observation. So this is application of Fourier analysis. It is developed by William Thomson, and there are many toolkits available to extract the tidal elevations and tidal currents. One of the popular tool is TAR, developed by PSML, PSMSL, and there are other software kits like Tidal based on MATLAB and UTide. In most of the program, there are freely available software kits to extract the tidal elevations. So here there is an example of the total this observation from the tide gauge, and this is the tidal prediction or the extracted tidal signals from the tidal software toolkit. This blue is the observation and green is the tidal component, and the red is the residual. This means the subtidal uh, subtidal sea level variation. And as I mentioned earlier, associated with this vertical movement of sea surface, there is currents, horizontal currents. It is called tidal currents, and these tidal currents are often expressed in terms of ellipses. So it is simply the it simply gives the orientation or the direction of the tidal flow and the maximum amplitude and minimum amplitude and the direction of tidal currents. So this semi-major axis of this tidal ellipse usually represents the maximum magnitude of tidal currents, and the semi-minor axis represents the minimum of tidal current, magnitude of tidal currents, and this orientation of this tidal ellipse gives the direction of tidal propagation. And one more thing is this tidal ellipse can be constructed for each constituents, like this for this major constituents, and also for the total tidal current for over a tidal period. So okay, so then we will move on to the numerical modeling of barotropic tides. So this modeling of numerical modeling of barotropic has a very vast applications, including the port areas and coastal areas for the safe navigation and tourism purposes, and often to estimate the flow in the narrow channels which is as near to the sea. So numerical modeling of barotropic tides comes with the development of computational power, digital computation. The first theory, the convincing theory of tides is provided by Sir Isaac Newton. So he was the first who proposed the tide generating force based on the gravitational theory and provided explanation for the cause of tides. So in his theory, he just considered the earth is covered with full of water, and depth is uniform, and there is no continents in the ocean. So based on that assumptions and the gravitational theory, he able to provide convincing explanation for the tidal oscillation and tidal generating forces. But those were equilibrium. This is known as equilibrium theory. So this theory was not uh, uh, good for practical application, and it was not explained most of the properties like amphidromic point, where the tidal amplitude is zero in the open oceans, and the different nature of tides at different areas. So later, Laplace, a French mathematician, introduced the dynamical theory of tides by considering the dynamical nature of tide generating force and its rotational effects, gravity, and the non-uniform depth of the ocean and continents. So he formulated the equations, hydrodynamical equation for tides known as Laplace tidal equations, and he explained many realistic features of tides in the ocean basins, including apothermic points. However, the solving the Laplace tidal equations was difficult without simplifying the equations. Therefore, the prediction of tides based on simplified LTE Laplace tidal equations in the coastal region was not accurate for the practical applications. Though the accuracy of tidal predictions increased with the emergence of numerical models associated with the emergence of computational power and computational facilities. The phenomenal progress in the study of tides was made with the emergence of numerical ocean model using digital computers in the second half of 20th century. So many researchers attempted to derive solutions for this LTE Laplace equations and prepared global maps of the oceans. So the initial attempts on global tidal modeling were focused on the mapping of semi-diagonal tides, that is major constituents such as M2 and S2 in the open ocean using coarse grid resolutions with a grid resolution of 1 to 2 degree, while and the shallow coastal areas were ignored. So using these assumptions during late 19th 20th century, so many authors or many researchers developed maps for tidal elevation in the global ocean. So the modeling of tidal elevations and tidal currents is based on the vertically integrated continuity equation and equation of momentum. So tides are shallow water waves. So we can use the tidal shallow water equations to model the tide. So here tide, we are considering tides as barotropic, and there is no vertical variation in currents and temperature or salinity. So using that assumptions, we can model the tidal elevation and currents reasonably well in the coastal areas and open ocean. So these are the basic equations. The first equations gives the continuity equations, and the second equation is gives the momentum equations with assumptions of uh, vertically integrated equation. That means there is no vertical variation in currents and temperature. So this first terms represents the rate of change of currents U component, and its these two terms give the advection terms, and this Fe represents the Coriolis terms, and the first term on the right hand side represents the pressure gradient, and this is the frictional terms and viscous term. So the numerical solutions of these equations are obtained by discretizing the equations in space using an explicit finite difference scheme over numerical grid and time. So this model required a bathymetry and depth and initial state, but it is usually taken as 0. So this this momentum equations will be discretized into this horizontal grid using numerical schemes such as finite difference or center difference schemes. So for tidal model, the forcing data will usually be known edge of the model is given in the boundaries like here. So this is the horizontal model example of a model domain, and here these areas are land and it is closed, and this area in the west is open. So you usually give the tidal forcing in the boundaries as boundary conditions. Okay, so using these numerical models, Park and Hender were the first who derived a more realistic maps of M2 and K1 tides in the global oceans. This is the in 1980. So this is the tidal map of tidal amplitude is developed by Park and Hender in 1980. So it gives the overall picture of the tides, but the accuracies were very less, and their maps able to their model able to uh, capture all the basic features such as amphidromic points and the phase variation in the global ocean. Here, uh, and in order to obtain the more accurate tidal solutions, further research has been done, and one of the research is Sardowski in 1980, who adopted a novel approach, that is assimilation of island and coastal tide gauge data into the hydrodynamic model. So it is data assimilation basically. So which was a major milestone in the global tidal model. So this in the figure in the bottom, this left side shows the tidal map produced by Swarovski in 1980. It is a more realistic and very close to the present map of tidal amplitude in the ocean. He assimilated about 2000 coastal tide gauge data into the global hydrodynamic model with a grid resolution of about 1 degree, and prepared global charts for 10 major tidal constituents, including diurnal, semidiurnal, and long period tides. So, which was the first reliable global tidal solutions from the numerical models. So, however, these models were produced tidal maps. The inaccuracies in the bathymetry and poor representation of coastal and shallow regions in their models limited the use of uh, the simulations or the uh, solutions into the coastal and geophysical applications. So later, a better understanding of global distribution of tides and unprecedented increase in the accuracy of global tides were achieved by the uh, emergence of satellite altimetry. So satellite measures the sea surface height, and from that we can derive or extract the tidal elevation along its tracks. So in 1990, Cartwright and Ray extracted the tidal signals from the satellite altimeter observation obtained from GeoSat satellite, and they prepared tidal maps using the satellite measurements. Even though the tidal solutions from the geosat were better than the numerical models at that time, it had limitations due to the short data record and orbital errors. Later, more accurate global maps were available with the launch of high precision altimeter missions such as Topaz Poseidon in 1992 and followed by Jason 1 and 2. So many researchers used this data and prepared more accurate global solutions based on altimeter observations. So before going to detail into the paratropic tides and its global maps, I would like I give that how to extract the tidal signals from the altimeter. So tides have diurnal and semi-diurnal periods, but satellite repeat cycle is about couple of days. For Topaz Poseidon, it is about 10 days. So the tidal signals cannot be directly extracted from the at satellite measurement. So to overcome these limitations, a method called tidal frequency aliasing is used to extract the tidal elevation from the satellite data. So we can alias the short period tidal period into a long period. So this image gives the picturization representation of frequency aliasing. So this method is known as frequency aliasing. For top expositor missions, aliasing period is about 62.11 and 58.74 days for M2 and S2. The actual period of M2 is about 12.42 hours, but to extract the tidal amplitude from the satellite data, this tidal period is aliased to 62.11 days. So this aliasing frequency is computed with the relationship of tidal period and the interval of satellite data, like the acoustic interval frequency of satellite data. This equation can be used to extract the or alias the alias tidal frequency to any particular period based on the sampling interval. So based on the satellite data, Egbert et al. 1984 prepared the global tidal solutions known as TPXO using assimilation of satellite data into the hydrodynamic models, and it was updated in the following years. So this is the this was the most accurate tidal solutions, which because it uses assimilation of satellite data and all other data into the hydrodynamic model. In the following years, this TPXO is updated, and it can be. I think the current version is TPXO 11 or 10. It is not given here. Okay, you can download that data from the official site of TPXO tidal model, and using that tidal solution or tidal data from the altimeters, many of the features or energy budget of tidal tides in the ocean were estimated. So more accurate estimation of barotropic tidal energy flux was the one of the updation. This is the mean tidal energy flux from M2 barotropic tide determined from TPX of Poseidon altimeter, and we can see that this strong tidal energy flux through the narrow channels in the Indonesian and the area between the Australia and New Zealand. So based on using this data, the tidal energy fluxes were estimated, and it was more accurate compared to other estimates at that time. And one of the other important results or the significant advances in the tidal research was the identification of tidal energy loss in the open ocean. So earlier it was believed that most of the tidal energy is dissipated by means of bottom friction in the shallow areas and shallow bays. But using the satellite data, Egbert and Ray identified significant loss of tidal energy in the deep ocean. It accounts about 33% via internal tide generation. That means over this steep topography or seamounts or mid-ocean ridges, a significant fraction of tidal energy, barotropic tidal energy, is converted into the baroclinic part. That means it will give rise to the generation of a particular kind of wave in the ocean known as internal waves. So this is the TPXO global tidal models. It's a series of fully global tidal model, which best fits in a least square sense the Laplace tidal equation and altimetry data. Each next model in TPXO series is based on the updated bathymetry and assimilates more data compared to the previous versions. This is the global map of M2 tides from the TPXO model. So TPXO model gives a complex amplitude of mean sea level, amplitude of tidal elevations and transport, and for currents and elevation for the 8 primary constituents and 2 a long period and 3 nonlinear harmonic constituents. So this data can be freely available from this TPXO website. So other than this TPXO model, which was based on satellite altimeter, there are also many other global models such as GOT 99.2 and FES 2004, which are developed in the following years by data assimilation, higher horizontal resolution, and inclusion of more tidal constituents. This is the tidal amplitude prepared from the OTPS software. So there is a software called OTPS or OSU tidal prediction software. We can download that OTPS software and use the TPXO data to generate the tidal amplitude and tidal currents all anywhere in the global ocean. I think okay, if anyone interested, I can show how to extract the tidal elevations and from the TPXO model, but I did not included that part in this lecture. So apart from this is the map from the GOT model, and this is map from the FES model. So both models gives almost same pattern. Most of the patterns will be same, and the accuracy is also in match. So in now the open oceans tides can be predicted with an accuracy about 1 to 2 centimeter, and in the near coastal areas the accuracy will be lesser. And parallel to this development of the satellite-based global tidal solutions, pure hydrodynamical models with the finite element mesh with the higher grid resolutions in the coastal and shallow seas are also developed. So one of the work was done by Provost et al. 1994, in which they used finite element hydrodynamic model with the data assimilation of altimeter data and derived more accurate tidal maps. So it is later. And next important development of the global tidal modeling was a combined use of satellite altimeter data, coastal tide gauges, and hydrodynamic models by using data assimilation techniques. Now most of the these hydrodynamic models use or solutions use all this data and prepare the better global tidal maps. So for the practical applications, we usually use the depth integrated equations, momentum equation and continuity equation for the tidal modeling. So this is an example of model domain which was prepared by Sindhu et al. So you can see that this northern part is closed. It is bounded by the landmass, and the southern and western part is open. So here the tides are for the regional purposes. We usually give the tidal forcing at these boundaries as tidal elevation and currents. So the initial condition we usually set 0, and the tides at the boundary we can give as a time series along the boundaries, or as amplitude or phase of the tidal constituents. That means the spectral values also we can give. from the global models. So either time series or the amplitude and phase of tidal elevation or currents at the boundaries. So for example, for ROMS, regional ocean model, we can give both elevation and currents all along the boundaries from a global tidal model, and it will simulate the tidal elevation and tidal propagation to this. And in some models, arts examples, ArtCirc and FECOM, we can simulate tides with tidal elevation also. And for regional applications, usually will use the tidal elevation or boundary currents uh, in the boundaries. But for the global tidal model, the tides are usually provided as a body force or equilibrium tide. Uh, so it will be given directly to the momentum equation or as a body force. And okay, so these are the summary of the barotropic tides as we discussed. So tides are the periodic rise and fall ocean surface caused by the gravitational force, and is tidal oscillation are combination of waves having different frequencies known as harmonic tidal harmonics. So this origin of these constituents are linked to the relative position of the rotation of sun and moon and earth. The dominant frequencies are half a day and day, 1 day, and main constituents are semi-diagonal constituents M2, S2 and N2, and diagonal constituents K1 and O. So it is estimated that tides lose about 3.5 terawatts of energy in the ocean. So most of them dissipate by means of bottom friction. About 2.5 terawatt of energy out of 3.5 is dissipated by means of bottom friction. But in the rest of the portion, the conversion of barotropic tides over the topography occurs. So the tidal current, when the tidal currents flows over the steep topography, that some of the energy will be converted into some other form. So that we will discuss in the next few slides. So this baroclinic tides generates when the barotropic tides flows over a steep topographic gradient. So these are simply internal gravity waves or internal waves at tidal periods generated due to the interaction of barotropic tides with the steep topography. Once these waves are generated in the ocean, uh, it will propagate as gravity waves. Note that in the previous slides, when we discussed about barotropic tides, we assumed that we assumed that the vertically averaged, that there is barotropic condition. That means there is no variation in vertical gradient of temperature or density and uh, current. So now we are introducing that realistic nature of ocean. So it has a variation in density or depth. So that brings a stratified condition. So ocean is stratified. So what will happen when the barotropic currents flows over a steep topography in a stratified ocean? So that's what here we are looking. So when in the presence of stratification, so there another form of waves are generated in the ocean. This is known as internal gravity waves. So these waves are like simple gravity waves as we see on ocean surfaces, but these waves will be having the existence only if the water is stratified, and it is the interior, it will exist in the interior ocean. So that's why it is called internal tides. So the presence of these waves can be detected from temperature and velocity measurements in the ocean. For example, this figure here represents the time series of temperature observation from a moored buoy. Here we can see that this temperature oscillations to up and down oscillations of isotherms in over a day. So, and there is a period where the tidal these oscillations are very strong, and there is a period where this vertical oscillation of these temperature surfaces isotherms very small, and again a relatively large period of uh, isopycnal surfaces. So these are essentially due to the spring and neap cycles of tides. So uh, uh, like similar to the barotropic tides, internal tides also follows the spring neap variability of in most of the locations. There are exceptions that we will discuss in the coming slides. Here what we can see that this simple gravity waves is exist in the inside the oceans, and it can propagate vertically also. In the the waves what we are seeing on the surface of the ocean mostly propagate in a horizontal direction, and here these waves can uh, propagate vertically and transfer the energy into the deeper layers of the oceans. One of the important significant consequences or significance of this internal tides in the ocean is ocean vertical mixings. When these internal waves breaks in the inside the ocean, it will cause in mixing, strong vertical mixing, which provides about half of the energy for interior ocean mixing in the ocean, and it is also help to maintain the observed stratification. These internal waves also have important application or role in nutrient distribution and biological productivity and ecosystem. Similar to that, sediment transport and sound propagation and offshore industries. So this when the strong vertical oscillations of the isopycnal surfaces can uplift the submarine uh, cables, submarine cables, as well as the offshore drilling uh, platforms. So these internal tides are very important in uh, this safe conduct of these offshore industries. So the identification of those uh, and prediction of internal tides is very important in navigation as well as offshore industries. Uh, so the propagation of internal tides in the ocean can be detected from the satellite altimetry also. So the studies shows that internal tides in the ocean can propagate thousands of kilometers without much dissipation. Here what we can see that this is the propagation of internal tides from the Hawaiian Aleutian ridges in the Pacific Oceans. Here we can see that these patches represents the amplitude of or of the internal tides, surface amplitude of internal tides, and it propagates about thousands of kilometers in, yeah, I will take a break for 5 minutes and we'll continue after that. I hope now I'm audible and the screen is visible to you. Okay, as we discussed, so these internal tides can propagate thousands of kilometers all across the ocean. It is estimated that about only 30%. Okay, it is estimated that only 30% of the energy is dissipated near to the generation sites, and most of the energy propagate, or the internal tides propagate away from the generation site and distribute the energy into the remote areas. So this propagation of this that accurate modeling of these internal tides and its propagation is very important in numerical models, because it has significant effects on interior ocean mixing in the near field as well as away from the generation sites. It is estimated that about half of the internal internal wave mixing in the ocean is provided by the tidally generated internal waves. So when this internal tides, as I mentioned that the internal tides can be propagate vertically in the ocean. So it can be seen as a beam in the velocities, and it transfer the energy from the vertical direction. When it reaches the bottom, and it again reflects back to the surface. From the surface again it reflects back to the uh, bottom. So this reflections and this beam like propagations can be seen mostly near the generation sites, where the higher vertical modes of internal tides are uh, larger. So as the distance increases, this beams disappears, and it will be like a pure first mode structure. uh, it will be having a maximum uh, flow in one direction in the surface, and uh, another direction in the bottom. So this is a, like, it will be like a first mode structure in the ocean. uh, when these internal waves propagate very large distances in the oceans, and it eventually encounters with distant continental slopes. So when these continental slopes very steep, these incoming internal tides will reflect back to the interior oceans. When the slope of this topography or continental slopes, and the slope of, slope of internal wave characteristics are same, it can uh, it will break, and it can generate the turbulence in the continental slopes, or even it can scatter the internal tides into higher modes. Uh, when the slope is very gentle, the topographic slope on the continental slope is very gentle, it can propagate further up to the shelf and dissipate inside the continental shelf. So there are many areas where the internal tides that reaches the continental shelf, and there are many areas where the internal tides reflects back from the continental slope. This is all based on the gradient of this topographic slopes in the continental slope. So there were many modeling attempts initially to study the internal tides numerically. So the most of the initial attempts were the internal tides across oceanic ridges and continental margins, uh, using 2D models. and like it is only 2D model means only one direction in is x and z with the realistic stratification and depth. 2D models were, for example, 2D models were used to simulate internal tide in Malayan Shelf and Bay of Biscay. These studies identified that onshore propagation and offshore propagation of internal tides from the shelf break and beam lake propagation of internal tides due to the scattering of internal tides into the higher vertical modes. So there are later many authors or researchers implemented 3D models to study the internal tide generation at many regions around the world oceans. And now one of the first global models of internal tides is provided by Arabic et al. 2004. He used global models to simulate the internal tide generation and propagation with the realistic bathymetry stratification conditions. He used a 1/4 degree model and he calculated the energy dissipation and conversion in the global ocean. This figure represents the global map of internal tide propagation from the Arabic et al. 2004. Here we can see that there are very strong internal tide generation areas in the deep oceans, especially in the Pacific. These are the Hawaiian ridges. From here, that internal tides can be generated. Internal tides will propagate thousands of kilometers away, and there are strong internal tide generation in the Western Pacific near to the East China Sea, the Luzon Strait area, or South China Sea. So from these areas, very strong internal tides are generated and propagate all across the Pacific. In Indian Ocean, this masculine ridges and near to in the eastern Indian Ocean, there are strong internal tide generation sites, and also in the southern part also there are few ridges and islands which submarine ridges and areas which cause the strong internal tide generation. In the northern Indian Ocean, so the internal tides can be is generated all along the west coast of India and Andaman and Nicobar island ridges. Along the east coast, the generation is very big. So, I will give some recent research on internal tides and barotropic modeling conducted along the Indian coast. So, along the west coast of India, the tidal currents are very weak in the relatively weak in the southern part, and tidal currents or tides increases from the south to north. In the off Mumbai area, the tidal currents even reaches the magnitude of about 30 to 40 meters in the shelf area. The magnitude will be even larger in the near coastal areas. These are the tidal currents from the shelf at a depth of about 100 meter, and this small wiggles is the amplitude of internal tides extracted from the satellite altimeters data. It is seen that near to these continental slopes, the amplitude of these internal tides is larger, and it is very weak or small in the central Arabian Sea or away from the continental slopes. So this modeling, this works conducted by Subish, and he shows that the most of the in barotropic to baroclinic conversion, the internal tide generation occurs over this area in the northern part, this continental slope, and also the topography, steep topography associated with the Lakshadweep islands. These two areas are the potential internal tide generation sites in the west coast of India. From this region, they showed that the internal tides propagate offshore into the deep Arabian Sea. Here also we can see the different internal tide propagation in the southern part. Here the internal tides generation and propagation is a little bit complicated due to the presence of multiple generation sites. So they showed that with this shelf break and slope region in the northern part and southern part account about 50% of the internal tide or barotropic baroclinic conversion in this region. Okay, similar to that, in the eastern east coast of India, there are observations and numerical studies on internal tides and barotropic tides. The tidal currents in this area are relatively weak compared to west coast, and studies shows that most of the internal tide observed all along the east coast of India is coming from the Andaman and Nicobar Islands, especially in the northern part of the Andaman and southern part of the Andaman. The internal tides generated at this area propagate all the way to the east coast of India, and it is estimated that about 80% of the energy observed all this east coast of India is coming from Andaman area. And this is the animation of internal tide propagation in this Bay of Bengal. You can see that there is a strong generation in the head bay and all along the Andaman Nicobar ridges. From this head bay, this arc-shaped source can be seen in this animation. From this arc-shaped internal tide source, the internal tide propagate and converge to the north central Bay of Bengal. So, yeah. So the convergence of internal tides occurs in the north central Bay of Bengal, and there strong internal tide activity can be found, and it is also observed in the satellite altimeter data. And the energy budget also estimated in the Bay of Bengal using numerical models. This shows that about 90 gigawatt, about 28% of the 28.5% of the internal tides in this area is converted as internal waves, and all these waves results strong dissipations in the entire Andaman Sea because of this internal tide breaking, and it is also shows very strong variability over a spring neap cycle. During spring tide, the internal tide generation is strong in this area and weak during neap tide. So the internal tides generated here at the Andaman takes about 5 to 7 days to reach along the east coast of India. So what we observed is most of the internal tides coming from the Andaman reaches after 5 to 7 days later, and it coincides with the neap phase of the barotropic tides. And it also the propagation of internal tides from these strong generation sites in the Andaman ridges also affected by the variation in mesoscale circulation. So the path of the internal tides changes due to the variation in the mesoscale circulation in the central bay. So such changes in the central bay results the changes in the arrival of internal tides along the coast. And so it is observed that the intra-seasonal variability in internal tide activity uh, along the uh, western bay of Bengal is resulted by the changes in the mesoscale circulations. So as a summary, so I just gave a basic idea of tides and modeling and satellite observation and modeling of internal tides and satellite observations and of internal tides and internal tide energy budget. So I would like to again give few more details about the observation of or analysis of internal tides and separation of from the uh, ADCP or HF radar data. It is shown we can use harmonic analysis or bandpass filters to extract the tidal currents from the ADCP as well as HF radar data. So it will give the vertical structure of tidal currents. So we can distinguish the tidal currents or barotropic tidal currents as a depth averaged uh, flow and the internal baroclinic or internal tide current as the difference between the depth average and total tidal currents. So it also important note that the extraction of tidal currents from the surface data or point data will be difficult. It means that it can contain both barotropic component as well as internal tide component in currents. So it should be you should be cautious about the tidal currents, whether it is associated due to the internal tides or the astronomically forced barotropic tides. So yeah, thank you for this is for the references. And if you need any assistance relating to the model internal tide modeling or barotropic modeling in ROMs, I can help. You can reach me in my Gmail ID, Jithin oceanography at gmail.com. So thank you all for watching. Thank you.
Questions in chat box.
Okay, I'll check. Okay, we have some questions. One question is, in the barotropic tidal modeling equations, we are neglecting the vertical variation of currents, and then why we are considering the viscous terms in the equation. Viscous terms we are considering only in the horizontal direction. So that's why we are using that in the modeling equations. next question is, yeah, I think he already answered that question.
Yeah, 1 meter.
And one other question is, can we use satellite data directly as for modeling? What is the accuracy we can get by satellite model? We cannot directly take that data because the satellite data is not a spatially uniform, or it is not a spatial data, like it's a long track data. So it will be it is difficult to take use that data alone in models. So it is better to use already these data are taken by these these agencies. Satellite data are extracted using different methods and provided really by many operational agencies. So we can, it is better to use their models or their solutions, because it's more accurate than uh, our numerical simulations or our own models. So now, right now the accuracy of the tidal model or the satellite derived model is about 1 to 2 centimeter in the open ocean, but in near coastal areas it is lesser, maybe 4 to 5 centimeter error will be there. But it is updating yearly, I think. So I think in future that accuracy will be more, and more with the availability of accurate satellite observation or more observation in all coastal areas. So uh, now there is new one of new satellite mission, SWOT mission. There it is very high resolution. It will provide very high resolution satellite altimeter data. So in future we can expect more spatial coverage of that satellite data. How do you, one other question is, how do you measure internal tides, or which website can I extract the internal tides data? uh, you are not mentioned from which source you want to measure, like for example in the ocean you can the signals of the internal tides can be found in temperature, currents, and even in the sea surface elevation. So most of the easiest way is to calculate or measure the internal tide is from moorings or buoys. So it have a temperature sensor as well as ADCP. So in that way you can measure the internal tide signals, but you need a very high high frequency measurements, at least with an interval of a day. So if you have that data, you can extract from the internal tides from the measurements. So what is the accuracy? So, or which website can I extract the internal tide data? Uh, Now, I don't think there is a direct site which you can download the internal tide data. But there are some few papers on satellite altimeters, internal tides on from satellite altimeters from Sahu et al. 2020 or something. You can download. They have prepared the uh, internal tide solution for the global ocean. You can download that data from their uh, site, or you can request directly. If you contact me directly, I can give the that related article. Another question is, 1 second. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Another question is any other methodology to assess the internal tides? Means change in coastal features or wave pattern. One other method is we can use radar images for identification of satellite data near the coastal areas. During the propagation of these internal waves, you can see the changes in reflection in the surface. So in satellite images, you will see the internal type crust patches or trough and crust as patches. So using that data, you can extract the wave fronts and its propagation direction from the uh, radar images. Another question is can mean sea level rise change the amplitude range of tide at a location? Yes, I think there are few recent studies on that one. Especially it was conducted on in the European shelves, I think. Uh, and they have identified and reported this mean sea level changes can introduce the changes in tidal amplitude and ranges in the global ocean. So another question is, does this contribute in releasing of heat like cyclone or tsunami too? I think the question is referred to the internal tide mixing. It should as this mechanical energy really breaks. It should release heat, and it will. But the amplitude of this or the magnitude of this mixing or the heat release will be very small compared to cyclones, and mostly occurs in the uh, interior ocean. So it will cannot be compared to the heat like cyclones, but it maintains it is very slow process, and it happens all across the global ocean. So because of that, the total magnitude is very uh, significant uh, in maintaining the vertical stratification and temperature, or even it contributes to the thermohaline or it have important implication on the thermohaline circulation in the global ocean. Okay, I think. Okay. Okay, I will check. Jitu. Another question is how these internal tides and currents affected by freshwater flux. Uh, yeah. As this freshwater flux can increase the sea surface stratification, near surface stratification. So it has a direct influence on internal tides. And the other way is if the internal tide mixing uh, can can enhance the distribution of this temperature distribution and salinity distribution. So in that way, these internal tides can affect by freshwater flux. And one other thing is, there is some studies which indicates the refraction or the advection of internal waves due to the current. So if the currents are very strong, it can change the internal tide, and it's the propagation. For example, as I showed in the slide, if there is a very strong mesoscale currents, it can change those currents, and associated change in stratification change the direction of internal tide propagation in the ocean. Another question is, did monthly sea level data from PSMSL contain any low frequency tidal signals? I'm not sure about that data and its processing, but I think there will be accounted those low frequency variability. But however, even though uh, that periodic changes will be very the long period changes will be very small, uh, so it may not be affecting the linear trends in the uh, data. And I think that's all. Okay, I think that was the last question. Oh, sorry, one more question is there. How do you validate the results? I think this question is like meant by how to validate the model simulated tidal currents or internal tides. The best way to compare the model simulated internal tides or barotropic tides, to compare the tidal constructed tidal ellipse for both barotropic and internal tides, and compare that its major semi-major axes, minor axes, and inclination and phase. So that way you can validate that one. And for internal tide from satellite also, you can validate from model simulated sea surface heights by extracting the data along the satellite tracks. And other ways to do the harmonic analysis of model simulated data and extract the tidal periodicity for both barotropic and internal tides, and do the same for observation and compare the amplitude and phase. And also you can compare the time series of currents extracted from the harmonic analysis from both model and observation. I think that's the
Yeah, one more question is there, no? Last one.
last one.
Can
Okay, one more question is there. Can the propagation of these internal tides be seen on the ocean surface? SAR images are the only tool for that. The propagation, if you want to see the visual observation, like visually, I think the SAR is the only options. Uh, I think, but there is there are its signature in the surface elevation. From the satellite altimeter, you can get the amplitude of internal tides. So that way we can see the propagation and its phase. Calculate the phase of internal tides from the satellite altimeter along the tracks. Then you will be able to identify the direction of propagation. Apart from that, I'm not sure how we can see the uh, propagation of internal tides in the surface. Uh, I think that's all. I think that was the last question. So thank you all for watching and have a nice day.